This will be this will be a little bit of a short snippet, almost like an appetizer to a bigger video that I'll be making. But it'll be talking about Gaussian distributions, or the normal function as it's called, or the bell curve it's also called. So I guess to get kind of like an intuitive feel for what the bell curve is actually doing, or how we get the equation for the bell curve, we can start with kind of like a simple test, right? So if we start with, let's say, flipping a coin, right? We only have heads or tails. Heads or tails, and it's 50-50, right? 50-50 each. 50-50 each. So after one, right? After one toss, possibilities are head or tails, right? So if we draw like a cumulative probability graph, so all that is showing what the probability of getting each outcome is. Right? So if we draw a graph with the outcomes, right? This will be heads, this will be tails, and it's convention. It's conventional to make the area under the curve, right? So all this whole area, right? This whole rectangle, it's conventional to make the area equal to 1. And that's equal to 100%, right? So all the probabilities add up to 100%. So if the area is equal to 1, then the area of this guy, right, of only getting heads, it'll be 0.5, right? Area of tails, only 0.5, right? So that's if we flip, one time. There we go. That's if we flip one time. If we flip two times, there's 4 possibilities, right? But 2 of them will be identical, right? If we're talking about outcome, right? Not the order. So we're not talking about order, but we're just talking about outcome. So there'll be heads, right? Heads, and then this will actually be heads. Sorry, head. So let me make that a bit bigger. Let me make that a bit bigger. So the outcome can be head, right? Head. So 2 heads, or head, tail slash tail head, right? Tail head, one of each, or tail, right? Those are the possible outcomes. And the area will still, right? Area will still add up to 1. And so in this case, right, probability of getting head, that's 0.25, right? 0.25 or 25%. Tails, right? 0.25. And the middle part, right, since we actually have 2, head, tail, head, it's going to be 0.50, right? 0.25 plus 0.25, right? So it'll be 50%. And if we actually keep repeating this, right, we can keep going further and further and further. So with 3, there will actually be H, 2 head. So I'll write 2 head, 1 tail, right? Or 2 tail, 1 head. And then tail. So now it'll actually be, if you think of it like total possible outcomes, right? To make it just a bit easier, we have 2, right? We have 2 possible outcomes, right? So this will be 1/2, and this will be 1/2. We've got 4 possible outcomes for 2 flips, right? So this will be, we can write it 0.25, or we can write it 1 out of 4, right? 1 out of 4, 2 out of 4, 1 out of 4. Right? And that's just because we're just doing 2 to the power of however many flips, right? 2 to the power of 3 flips, that's 8, right? 8 possible outcomes. So that, and then getting 3 heads, that's 1 out of 8. Getting 3 tails, that's also 1 out of 8 chance. And then those 2 in the middle, if we go through all the possibilities, it'll actually just be 3 out of 8, 3 out of 8. And that'll be, just to make it more clear, right? That'll be for 2 heads and 1 tail, right? So it'll be heads, tails, right? Head, tail, head, and tail, head, right? So for 2 head, 1 tail, These are 2 head, 1 tail. And for 2 tail, 1 head, it'll actually, it'll be basically the same. You just have to flip all the H's to T's and T's to H's. And I'm going through this a little bit quick, just because I want it to be a shorter video, but you can see the pattern, right? If we have 2 heads and 1 tail, all you have to do is just move this tail around, right? And you get all the possibilities, right? So the tail's at the right side, the tail's in the middle, and the tail's in the left side. And then you just flip the H's for the T's, right? For the other possibility, right? And there's only 3. So we know it's going to be 1 out of 8 chance, 3 out of 8, 3 out of 8, 1 out of 8, right? And then we can keep going. But some of you might have spotted already, or might have already known, this is actually the famous binomial expansion, right? Pascal's triangle, right? Binomial expansion, right? Pascal's, this is exactly the same as Pascal's triangle, right? The 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, right? Going downwards, right? So you add up all the numbers that are above it. So you start with 1, then you add 1, 1. So you first start off with this small triangle, right? And the next layer down, you keep expanding diagonally, right? So all the diagonals are going to be 1, 1, 1, 1. But then in the middle, right? The middle is going to be the summation, right? Of the top 2 the numbers that are the 2 numbers that are above the number you want to get, right? So the 2 is equal to 1 plus 1, right? And then 1 is going to be the diagonal. 1 plus 2 is 3. 1 plus 2 is 3, and so on and so forth, right? This is the binomial expansion. No, very famous, right? Pascal's triangle. It's also used for like quadratics, right? If you have like x plus 2, and then if you do like the 4th, right? All you have to do is go to the 4th Pascal triangle, and you can plug in all the coefficients, right? So it's very, very handy. It's neat seeing all these connections, but as you might have guessed, this is, right, because we only have 2 possibilities, right? Heads, tails, right? Only 2 possibilities. This is the binomial function, or binomial probability, to be more specific. And there's actually a neat little formula for the binomial expansion. So let me write it down. So if we have n, there we go. Okay, so if we have n, let's go. Yeah, okay, that looks good. So if we have n is the number of times that we repeat the experiment. So in this case, right, it's flipping a coin, right? How many times we flip a coin, and if you have p, right, that's the probability, right? In this case, it's half, right? Half heads, half tails. You would have to specify which is p and which is q if you had a different, right? If it was, let's say, 40% for heads and 60% for tails, then you would have to specify. But in this case, they're the same. K is the number of occurrence, right? So how many times you get heads, right? Heads. Or you can do how many times you get tails, right? It just depends on what you define P as, right? How many times you get tails, how many times you get heads. You just have to make sure you just pick one. And then Q, right? Q is just the opposite, right? So it's just 1 minus P. Or, in this case, it's going to be 1 minus 0.5, which is 0.5. Which makes sense, right? The probability of getting, let's say, heads, 50%. Probability of getting tails is also 50%. And that makes sense. And so the binomial formula says, if you have all these variables, you can basically plug it into this formula, nck times p to the k times q to the n minus k. So all this is saying is, and if we go through this a little bit, so this is p to the power of k, q to the n minus k, and then n to the n choose k. And if we break this down a little bit, like let's say if we, I don't know, to make an example, let's say we flip it, we flip the coin 3 times, right? Flip it 3 times, and let's say we're looking at heads, right? So P is heads, probability of heads, which is equal to 50%, and K equals number of heads, right? Number of heads. Let's say we want to get probability that we'll get 3 heads, right? So okay, so it makes sense that if we have p to the power of k, that's how many times you get the outcome that you want, right? So in this case, we get heads, right? P to the k, right? So 0.5 to the power of 3. That'll give us the number of times we get the outcome that's desired, right? So that's why this makes sense. But then we also have to multiply that by the fact that we wanna also include the probability that we don't get the outcome we desire. So in this case, right, n minus k, n is equal to 3 times, so it's going to be 3 minus 3, right, because number of heads. But let's say if we wanted 2 heads, right, 2 heads, 1 tail, right, so 2 heads, 1 tail, right, because it's binomial, because it's a binomial distribution, if we know n, right, if we know n, which is 3, and if we know k, right, number of heads, which is, in this case, it's 2, we know the number of tails we also need, right? Now, if it's not going to be heads, it has to be tails, right? If it's not going to be tails, it has to be heads, right? There's only one other possibility, since it's, there's only 2 outcomes, right? That's why it's called binomial, right? Bi to nomial. I believe it means name. I'm not 100% sure, but it just means there's 2 outcomes, right? If there's 2 heads, there has to be 1 tail, right? There's no other possible outcome. So this makes sense, right? Q to the n minus k, this gives us the probability of getting the opposite, right? Get opposite outcome. P to the k, this gives us the probability of it giving the outcome we desire, right? P to the k. So it's heads 0.5 to the power of 2 and 0.5 to the power of 1, right? But then, as we saw earlier, right, there's multiple ways to arrange this, right? You could do HHT, HTH, or THH, right? There's multiple ways to arrange it. So now that n choose k, right, now all that's saying is how many combinations are there, right, of n given k, right, given k. N is going to be the total number of flips we do, right? So there's three outcomes that we get, right? Because we're flipping 3 times, right? And n choose k, right? Because this 2 heads, right? 2 heads is the outcome that we desire, right? So based on that, how many ways are there to arrange the h and t's, right? That's what n choose k is showing. And I'll put it in the description, but there's also a formula for computing combinatorics, right? Choose k, which I'll post in the description below, because I don't want this video to get too long. But because of that, right? Because there's 3 possibilities to arrange 2 h's and 1 t. Now we know that the probability, right, is p to the k times q to the n minus k, which is 0.5 to the 3, which is 1/8. right? 1/8, and then there's 3 times 3 possible ways to choose k based on n. So we're gonna get skipped a couple of steps, so we're gonna get 3 out of 8, right? Exactly the same as we got earlier. And that's just to show why this function works. But the more cool part, right? The very cool part is actually, right? What happens if we, keep on doing this, right? 4, right? If we flip it 4 times, if we flip it 5 times, right? Da 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 da. Limit, right? In calculus, right? If we take the limit as n goes to infinity, what are we gonna get? We're gonna get the bell curve. That's right. We're gonna get the bell curve. And I'll talk about this the next video.